So we want to take what we learned about the derivative of inverse functions and now apply that to the derivatives of the inverse trigonometric functions. So let's do a quick review on what we even mean by the inverse function of sine or the inverse function of cosine. So sine and cosine as functions are probably best defined in the following way. So if we have the unit circle, I'll do my best to draw a circle here. And we take a ray, making an angle theta with the positive x-axis. Then the x and y coordinates of the intersection point with the unit circle, we define to be cosine theta as the x-coordinate and sine theta as the y-coordinate. Okay, so cosine theta and sine theta, those are definitely both functions because for each angle we're going to get a unique output. But it's not the case that for each output we have a unique input. And that's because if I take cosine of theta and add 2 pi, so if I'm at theta and then I go all the way around the circle, so I add 2 pi, I'm going to end up to where I started. So I'm going to have the same x-coordinate. So this is cosine of theta. Same thing for sine. Sine of theta plus 2 pi is sine theta. So what's the point? I mean, the point is sine and cosine are not one-to-one. So at least over their natural domain, it does not make sense to talk about the inverse of sine and the inverse of cosine. So we need to do a domain restriction. So let's think about cosine theta first. Okay, so cosine theta is the x-coordinate. So let's think about which angles will give us kind of unique x-coordinates. So we see that starting here and going all the way over to here, we're kind of ranging through the different x-coordinates we can get in this fashion by intersecting a ray with the unit circle. So it looks like if theta is from 0 all the way to pi, we'll have a unique output in some sense. So we'll restrict domain to the interval 0 to pi. This is for cosine theta. Okay, and so on this interval, cosine theta is 1-to-1, right? Because for each angle, I'm going to have a unique x-coordinate. Okay, so you can just see that's kind of like an invertible process. So if I just am restricting here and I give you an x-coordinate, I can actually tell you which angle it goes with, assuming that my angle lies between 0 and pi. So we'll define cosine inverse of x to be theta, okay, where theta is the angle in this interval for which x is cosine theta. Okay, so we're just defining the inverse cosine of a number. And now, of course, this number needs to be between -1 and 1. It needs to be in the range of the cosine function. And cosine lies between -1 and 1 because the x-coordinates of points on the unit circle lie between -1 and 1. Okay, so we can do something similar for sine theta. But now for sine theta, sine is the y-coordinate. And so going from 0 to pi, this angle here seems to have the same y-coordinate as over here. So we don't want to restrict to 0 to pi because sine is not going to be 1 to 1 on 0 to pi. Actually, we want theta to be between -pi/2 and pi/2. Along this half, this right half of the unit circle, all of the y-coordinates will be unique. So for sine, we'll restrict the domain to -pi/2 to pi/2. Okay, and then we'll define sine inverse of y to be theta, where theta is the unique angle in this interval, -pi/2 to pi/2, such that the sine of that angle is the y-coordinate that we're interested in. Okay, so this is kind of the story with sine and cosine. Now, there's nothing special about the interval from 0 to pi, or the interval -pi/2 to pi/2. Now, they are maximal in the sense that we can't make these intervals any larger and still have cosine be 1 to 1 and sine be 1 to 1. But we could possibly choose a different interval. So for cosine, we could choose, for instance, pi to 2 pi. Or for sine, we could choose pi/2 to 3 pi/2. But these are kind of the conventional choices to restrict the domain of sine and cosine to make them 1 to 1. Okay, so in a similar fashion that we did sine and cosine, so here we see this table shows our function, our trig function, and then of course the inverse function. But in order for the inverse function to be well defined, we need a domain restriction. And so these are kind of the conventional domain restrictions that we use for these given functions to define their inverse functions. So we saw exactly for cosine why we use 0 to pi, sine we use -pi/2 to pi/2. But we can do something similar for tangent, okay? And something similar for secant, and something similar for cosecant, and something similar for cotangent. Now we could spend a significant amount of time actually breaking down what's going on with each of these functions. I don't think that's the best use of our time. But what we need to take away is that in general, trig functions are periodic, so they're not 1 to 1. So that's kind of the problem. So that's worth just kind of keeping in the back of your mind. Trig functions are periodic, hence not 1 to 1. Need domain restriction. To define the inverse function. And then these are kind of the conventional choices for those domain restrictions to make the inverse functions pass through. So now remember our conversation on derivatives of inverse functions. We kind of had this really nice fact that to find the derivative of the inverse of a function, what we needed two things. We need to know, well, first of all, the derivative of the function. And then second of all, we need to know the inverse function, or at least that the inverse function exists, okay, and kind of how it would be defined, even if we need to use some sort of domain restriction. But look at what we have here. For each one of these trig functions, we have a way to define an inverse function using a domain restriction, and we know the derivative of all of these trig functions. Therefore, we get for free the derivative of all of the inverse trig functions. So let's actually break it down and see how the derivative of these inverse functions goes through. Okay, so I have this really cool picture down here. I want you to ignore that for a second. We'll use it in just a minute. But first of all, this is what I want to do. I want to let y equal cosine inverse of x. Okay, so now recall what this means. Y is going to be the number between 0 and pi for which cosine of y is equal to x. Okay, so I'm just restricting the domain of cosine between 0 and pi so that actually this inverse function is well defined. So I would like to take the derivative of cosine inverse of x. How do I do that? Well, just like with e to the x and log x, I don't know anything about cosine inverse of x. The only thing I know is that cosine of y should be x, assuming that y is between 0 and pi. So I know that cosine of y is equal to x. Okay, and I want to know what dy dx is. Right, because dy dx will be the rate of change of the inverse of the cosine function. So let's use implicit differentiation. And that's kind of the name of the game for finding derivatives that maybe we don't know how to do from the definition. There's really no way we could find the derivative of inverse cosine just using the definition. We have to use implicit differentiation. So differentiating this equation involving y and x implicitly with respect to x, we have negative sine y. And then we use the chain rule, so dy times dy dx. And that equals 1. Okay, so we're done, right? Dy dx is equal to negative 1 over sine y. So what's the problem here? The problem is I would like the rate of change of y, which is an explicit function of x, to also be an explicit function of x. So what do we do? Well, here's where we're going to use this triangle. So I've set up this triangle in the following way. Notice that if y is an angle, so I'm thinking about y as being an angle between 0 and pi right here. Y is an angle, then to say cosine of y is equal to 1 is, in right triangle terminology, to say that cosine of y is equal to x over 1. I'm just using that trigonometric ratio, right? So the cosine, it should be the adjacent side over the hypotenuse. So if I have a triangle with the adjacent side x and the hypotenuse 1, then I can actually use the Pythagorean theorem to determine what the opposite side is. Okay, so why am I doing this? Well, I need to know what sine y is. But if cosine y is x over 1, adjacent over hypotenuse, then what is sine? Sine is opposite over hypotenuse. So sine of y should be square root of 1 minus x squared divided by 1, divided by the hypotenuse. But that tells me exactly what sine y is. So now the rate of change of y with respect to x, or in other words, the derivative of the inverse cosine function, is negative 1 over square root of 1 minus x squared. So it's kind of interesting that you take the derivative of an inverse trig function and you actually get kind of an algebraic function, right? So there's no trig functions here, right? It's just the quotient of the square root of a polynomial and then just 1 in the numerator. So it's really interesting that this happens. Okay, so I have another table for you. And I'm just going to say that following almost identical, or at least analogous, arguments of how we determined for cosine inverse of x what the derivative was, so negative 1 over square root of 1 minus x squared, you could follow that same reasoning for all of the other inverse trig functions. And I think we'll do a couple of them in the examples, just to give you a kind of more of a taste of how it goes. But here they are. Okay, so they're all sort of related. There's a very close connection between the derivative of inverse sine and inverse cosine. There's a very close connection between inverse tan and inverse cotangent, their derivatives, as with inverse secant and inverse cosecant. And the really cool thing that happens, so if you remember when we looked at the derivatives of the trig functions, we had a way to remember when we picked up a negative. And notice, really, that's the only difference between kind of these two very analogous inverse trig functions and their derivatives, right? So we just pick up a negative. But again, if it starts with a C, pick up a negative. And that's just one of those sort of coincidental things that happens in math. Is just the way things are named. It just happens to be the case that exactly the case when the function starts with a C, you get a negative when you take the derivative. And so that is a great tool to help you remember, especially if you're thinking about what's the derivative of sine inverse, what's the derivative of cosine inverse. Maybe I know there was something with a square root and a 1 minus x squared, but which one had a negative? Well, you can at least hang on to this kind of really helpful idea that if it starts with a C, you pick up a negative. Okay, so as an example, we want to see how the derivation of the derivative of tan inverse of x goes. So we have a very similar setup. And like I said, it's analogous to what we did with cosine inverse. So if we let y be tan inverse of x, what are the two things we know? We know how tan inverse of x is defined. This actually means that, well, whatever y is, within that domain restriction we had for tan y should be x. And we also know the derivative of tangent. So we're in a situation where we can do the same thing we did for the natural logarithm, what we did for cosine inverse, is basically rederive the inverse function formula. So we just implicitly differentiate this expression. So the derivative of tangent is secant squared. But because we're differentiating with respect to x, we got to multiply by the rate of change of y with respect to x. That's just the chain rule. And that equals 1. Differentiating x with respect to x just gives us 1. And so then we know that dy dx is 1 over secant squared y. But we run into the same problem. I mean, first of all, we're clearly not done because we're supposed to get 1 over 1 plus x squared. But also, I mean, the idea is that we want the rate of change of y with respect to x to be an explicit function of x, just like y is an explicit function of x. So we need to do something with secant squared y. So we're going to do the same trick we did before with the right triangle. So if we know tangent of y is equal to x, so if we let this angle be y, tangent of y equals x, tangent is opposite over adjacent. So x is like x over 1. So tangent of y opposite over adjacent, x over 1. So that's that ratio in this right triangle, the tangent ratio. But then just applying the Pythagorean theorem, we know that 1 squared plus x squared should be the hypotenuse squared. Or in other words, the hypotenuse is the square root of 1 plus x squared. But now we can find all of the trig ratios. But the one we're interested in is secant. We want to know what secant of y is, or specifically what secant squared of y is. So secant y, now secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant should be hypotenuse over adjacent. Square root of 1 plus x squared over 1. But then if we square it, what is secant squared y? It's simply 1 plus x squared, as we would expect if we were to get the right answer. So dy dx is simply 1 over 1 plus x squared. And there we go. Very similar to the derivation for inverse cosine, but we just mix it up a little bit. The idea of using this right triangle to kind of help us visualize what's going on with the trig ratio is very helpful. And actually, for the foreseeable future, like if you take calculus 2 and you deal with, again, these trigonometric functions, this sort of triangle just really helps you out a lot, I'll say. So the idea of just kind of going back to this right triangle trigonometry, even though we defined the trigonometric functions using the unit circle, this right triangle trigonometry is very helpful to see the relationship between the trig functions. So just so we really get a taste of all the ways finding these derivatives could go using this inverse function idea, let's find the derivative of secant inverse of x. So you know the setup by now. Let's let y be secant inverse of x. All we know is that means that secant of y should be x. And why are we doing that? Because we know the derivative of secant. So what is the derivative of secant? It is secant y times tan y. But of course we're differentiating with respect to x, so we need to tack on the factor of dy dx by the chain rule, and that all equals 1. All right, so we're basically done. Of course, we're not done, but we're sort of done. So the rate of change, or the derivative of secant inverse, is 1 over secant y times tan y. But I need to know what secant y and tan y are in terms of x to get my derivative as a function of x. So let's draw this right triangle again. We know that secant of y is x. And again, we can think about x as just being x over 1. So if here's y, then secant y is supposed to be x over 1. So that's hypotenuse over adjacent, secant. Because secant is reciprocal cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Then we can use the Pythagorean theorem. This squared plus this squared should equal x squared. So in other words, the square root of x squared minus 1. And you can verify that 1 squared plus x squared minus 1 is x squared. So now we've filled out our triangle. We can figure out exactly what dy dx is. Okay, so let's think. Now, secant y is supposed to be x. We know that already. And then tangent of x, or tangent of y, is square root of x squared minus 1, because it's opposite over adjacent. Okay, that looks good. But now there's one thing to consider. Notice that we have an absolute value of x right here. And now anytime an absolute value comes up, you should be suspicious that we're taking the square root of something squared. Or in some case, or in some way, there's kind of a plus minus situation going on that we need to consider. And I'll say that, the case for tangent and cosine that we saw, we didn't really have this subtle issue. And the issue here actually comes from the domain restriction. So you see we're almost done. I mean, if we plug in secant y and tangent y in here, then we're basically done. But look at tangent y. Tangent y is the square root of x squared minus 1. It could also be the case that tangent y is negative, right? So really, I could have a plus or a minus here for square root of x squared minus 1. But whether or not this is plus or minus is only going to depend on y, right? Because tangent of y will be positive for y in a certain range, and then tangent of y will be negative for y in a certain range. So let's actually look at the domain restriction for secant x. And so what it is, well, y is in the following set. So it's either between 0 and pi over 2, or it's between pi over 2 and pi. And of course, the reason it's not defined for pi over 2 is because cosine of pi over 2 is 0. So if we divide by cosine of pi over 2, then that's a problem. And so let's just think about this. If y is between 0 and pi over 2, tangent is positive. So if y is between 0 and pi over 2, tangent y is positive. But if y is over here, if y is between pi over 2 and pi, actually cosine is negative and sine is positive, then tangent y is positive. Okay? Or I'll say greater than or equal to 0, because it could be equal to 0. Okay, so that's good. So that actually tells us when we need to take the positive square root here and when we need to take the negative square root. A little typo there. Tangent y is less than or equal to 0 when y is between pi over 2 and pi. But now we also need to think about secant. Okay, so if y is between 0 and pi over 2, secant y is greater than or equal to 0. But if y is between pi over 2 and pi, secant y is less than or equal to 0. Okay, so this is just a huge review in trigonometry. I don't want to go too much into detail, but I just want to give you kind of a thorough explanation of why this absolute value is coming up. It's coming from the domain restriction, essentially. Okay, so let's just think about this. If y is between 0 and pi over 2, both of these quantities are positive. So remember that secant y is really equal to x, and then tangent y is really equal to square root of x squared minus 1. So everything's positive, right? If y is between 0 and pi over 2. What about if y is between pi over 2 and pi? Well, then both of these quantities are negative. This is going to be negative, and this is going to be the negative square root. But in that case, everything is positive again. So actually we're seeing that what's going on, secant y and tan y that are showing up in the derivative are always positive no matter what y is. So the way we fix that is we just put absolute values around x to say that actually even if x is negative, we're going to get a negative from the square root, so it's going to be positive. Okay, so it's just a very, very subtle part of this equation. That, okay, yes, it really is x times square root of x squared minus 1, but there's just a compatibility between the signs that actually help this to always be positive. So we just express that kind of lazily by putting the absolute value on the x. So there's the idea. There's the rate of change, or the derivative, of secant of x. So with this example, we want to highlight the point that we've found some new differentiation rules for the inverse trig functions, and they need to play nicely with the other differentiation rules. Okay, so now that we have, I'll just say this, I believe it's true. We've talked about all of the derivatives of all of the functions we're going to talk about in this course. Okay. So now we basically theoretically know how to take the derivative of any function. Okay, so even if there's some inverse trig, we also need to think about the chain rule, product rule, quotient rule, etc. If there's some logs, same thing. I mean, all of these derivatives could just kind of show up in a lot of different ways, but now we have the tools to tackle them. And so here we have an inverse trig function being composed with the function x squared. But this is no problem because we know what the derivative of inverse cosine is. So we just want to start from the inside out. So what's the derivative of inverse cosine? Well, it's -1. So remember, it starts with a c, so we get a negative, over square root of 1 minus the argument squared. But this time the argument is x squared. So this should be x squared squared, or x to the 4th. And again, this is just coming from, it's not just x squared, it's whatever I'm taking the inverse cosine of squared. So x squared squared, which is x to the 4th. Then we use the chain rule. Because this isn't just cosine inverse of x, it's cosine inverse of x squared, I need to multiply by the derivative of the inverse function, which is 2x. And so that's it. That's the idea. Just don't forget the chain rule. Now that you know all these nice differentiation rules, the chain rule always needs to be there. The product rule always needs to be there, as we'll see in the next example. Okay, so same story here. We have this kind of compound function. I see a product of two functions right there, t squared times tan inverse. And then we're also composing tan inverse with the function 2 over t. So let's get to work. First things first, we need to use the product rule. So this should be 2t times tan inverse 2 over t. That was the easy part. And then plus t squared times, okay, what's the derivative of inverse tangent? Well, it's 1 over 1 plus whatever I'm taking the inverse tangent of squared. So in this case, 2 over t, 2 over t, that quantity squared, and then times, what's the derivative of 2 over t? That's the chain rule. So that should be -2 over t squared. And just a reminder, I'm just thinking about 2 over t as being 2 times t to the minus first. So when I take the derivative, I bring down the -1, so it becomes -2. I subtract 1 from the power, so it's t to the minus second, but that's the same thing as 1 over t squared. Okay, and you know, at this point, you could probably simplify a little bit, but I am actually in the camp that says you really shouldn't simplify unless you need to, unless you're trying to do something with the derivative. But that's it. Okay, so we just use the product rule with these functions. We use the chain rule when we need to. And now we know, if we ever see an inverse tangent, what to do, because it's just a derivative of an inverse trig function.